Following on from some of the earlier videos, we've seen this. Whenever this thing here is satisfied, then we can say it's symmetric along the x-axis. When we've also seen this, whenever this thing is satisfied, then we can say it's symmetric along the origin. Now we need to consider this. Whenever this thing is satisfied, then we can say it's symmetric along the y-axis. But then we need to try to fully try to understand this. We need to understand this transformation. You see, this transformation is easy to understand. So that's a bit like this. Let's say we've got our function in Cartesian form, f of x equals x squared. This transformation here is easy to understand. This is very similar to this. So here you've got your variable plus or minus a constant. So you've got your variable, let's say x, plus or minus, let's say minus a constant. So this transformation is easy to understand. You simply slide everything across by 2. But now if you look at this transformation, you've got a constant take away a variable. So that's a bit similar to me giving you this. You've got your constant take away a variable. So you've got your constant, so that would be 2, take away your variable. Now this transformation is easy to understand. It's simply everything sliding across by 2. But then what does this transformation mean when you have a constant take away a variable? So we are trying to understand this. We are trying to understand this here. But in order for us to understand this, we need to try and understand this. Now this thing here, this transformation here is quite hard to understand. But then in order for us to understand this, let's try and make it simpler. Let's break this down to this. So you've got your constant, so let's say 2, take away a variable, take away this variable here. So we are going to try and understand this transformation, because this here, as it stands, is too complicated to try and understand what's going on. So we are going to break it up to this. So we are going to try and understand this in order for us to try and understand this transformation. Okay, so let's try and understand this. So hang on. So we are trying to understand this transformation, but as it stands, this is too complicated. Let's simplify the situation. Let's try and understand this. So that's this transformation here. Now, so let's consider our function f of x equals x squared in Cartesian form. So what goes in here? So that's like me asking you what goes along here at the 2 mark. So what goes in here would be you putting this into here. So that would be 2 take away 2, that would be f of 0. So it's you stealing f of 0 and then putting it into here. So what goes along here is really you stealing f of 0 and then putting it in there. As it seems like it's stealing this point and putting it into here. So what goes in here is really you stealing what was here and then putting it into here. Okay, so this point here gets moved to here. Okay, and then what goes in here? What goes in here would be you putting this 3 into here. So that would be 2 take away 3, that would be negative 1. So what goes along here would be you stealing f of negative 1. So that's this thing here. You're stealing what was over there and putting it into here. So that's like me asking you, what goes in here would be you stealing what was over here and then putting it into here. So and then what goes in here? Well, you would put this into here. So that's you stealing f of negative 2. So that's you stealing f of negative 2 and moving it across to here. And then what goes in here would be you putting this into here. So that will remain the same. But then what goes in here would be you putting this into here. So that would be f of positive 2. So what goes in here would be you stealing f of 2. So that would be this thing here, and then moving across here. So it seems as if what I'm trying to illustrate here is that this transformation, what it seems like is that you jump to your constant. So you jump to your constant, and then you've got to flip it. So what was negative? You would steal what was negative and moving it across here, and then what was over here, moves across here. It seems what this transformation seems like is you jumping to your point here, and then you've got to flip everything across. You've got to flip everything across here. So that's what it seems like. So what this in polar form, remember a flip in Cartesian form would be you doing this. That's a flip in Cartesian form. But a flip in polar form would be you doing this. So this here is positive theta, negative theta would be you. A flip in polar form would be you doing this. A flip in polar form would be you doing this. Doing this. That's a flip in polar form. Okay, so a flip in polar form would be you flipping it. Would be you flipping it this way. Okay, so this transformation, what it's saying is that it seems like you having to jump to your pi here, and then you've got to flip it. So what this transformation here, hang on, let me just put the hand back to normal. Bear with me. Bear with me. So this, as it stands, it seems like this transformation here, this transformation, you jump to your pi. So hang on. So what this transformation is doing is this. Oops. What that transformation is doing is this. You would rotate it like this. Bear with me, and then you got to flip it. So it's like this. Bear with me. So that's what it seems like. So this transformation here, it seems like you jump to this, to your point here, and then you flip it. So that's what this transformation here is doing. Or you can think of it like this. You start out with, or you can think of it like this. You start out with your whatever here. So this is your hand here. Bear with me on this, and then you apply this transformation. So that means you flip it. So now it's, I can't draw an upside down thumb. Where there? So this transformation here would be you flipping. So hang on. So this is your original. This is your f of theta here. When you apply this transformation, it flips it upside down. So your thumb would be down here. Can't draw it. So it's like this. And then you can apply this transformation here. Well, I can't draw it properly, but what this is doing is that it rotates it. There are two ways you can think about it, or maybe more. You can rotate it and then flip it, or you can flip it and then rotate it. So that's what this transformation is doing. Well, if you rotate it and then flip it, and it turns out to be the same as the original, then you can say that it's symmetrical along the y-axis. So what this is saying is that if you rotate it by pi and then flip it, and it happens to be the same as the original, then you can say that it is symmetrical along the y-axis. So let me try and illustrate this. Wait there. So if you have something like this, we're trying to illustrate this here. Pi take away theta equals the original here. The original. So what it's saying here is that suppose you have this thing here which happens to be symmetrical. Okay. So if you apply this transformation, let's just look at this quadrant here. What this is saying, if you apply this transformation and it equals the original, then you can say it's symmetrical along the y-axis. Because hang on, let me clear this and do it again. Let's consider this this symmetrical. This here, as it stands, is symmetrical. If we apply this transformation, pi take away theta, and it happens to be the same as the original. So let's just consider this transformation. So let's just consider this quadrant here, this first quadrant. If we're going to flip it, so that would then give us this. That will then give us this, and then we're going to rotate it we're going to rotate it by pi. If you rotate this quadrant here, it will give you the exact same original. So therefore, this thing, I hope you can follow this, because if you applied it, let me start again. Hang on. Let me start again. I hope you can follow what I'm trying to illustrate here. We are trying to, whenever you apply this transformation and it equals the original, then you can say the whole thing is symmetrical along the y-axis. So let's consider a symmetrical and already symmetrical curve here. Let's just look at the first quadrant here. Now let's apply this transformation. So we're going to flip it. So this transformation really means we flip it. So that will then give us our curve looking like this. Now rotate it by pi. So that will then give us this line here. And this line here is the same as the original. So therefore, if when you apply this transformation and it equals the original, then you can say that the curve is symmetrical along the y-axis. I hope you can follow this.